All right. So this next unit that we're going to be talking about, or I guess it's the book calls this Module 2, the next topic we're going to be talking about is absolute value functions. Remember, when we talked at the beginning of the year, we talked about this course being like a survey of function groups. So throughout the year, we're going to be focused on this idea of functions. That's what the introduction was. Our first chapter that we just got done taking our test on was all about functions and properties of functions. Now we're going to talk about specific function groups. This first function group we're going to talk about is the absolute value functions. The three major skills that we're going to look at inside of each of these sections are simplifying, solving, and then graphing. Everybody okay with that idea? So today we're going to do a little bit of introduction about what an absolute value is, like what are the rules that we can use to simplify absolute values, and we're going to start talking about some graphing topics today. So that's the plan. So each time we start a new class of functions, these are going to be the three major skills that we're going to want to develop when we talk about these classes of functions. So just kind of keep that in the back of your mind, that by the time the test rolls around, the skills that we're going to be testing on are going to be your ability to like simplify and solve and graph primarily. There might be some additional like things along the way, but the primary skills that are going to be the same skill throughout the entire year are going to be these three skills. And now the details involved with these are going to change depending on the function type, but the overall idea or goal would not. Everybody okay with that idea? So we're talking about these absolute value functions. Let's start with a definition. So when we say absolute value, the symbol that we use is we have a vertical bar and then something and then another vertical bar. So if I'm talking about the absolute value of x, I'd write vertical bar, x, vertical bar. So the definition for an absolute value is it's the distance between 0 and whatever the thing is you're taking the absolute value of on the number line. What can we say about the sign of a distance? Distance is always positive, right? If I asked how far away from me are you, and you answered -5 miles, I'd look at you like you had a third head, right? It's not really a sensible answer to that kind of a question. Even if you're like the opposite direction from me, you're still 5 miles away. It doesn't matter the direction. It's distance is distance. It's always positive. So, in other words, what is the absolute value doing? Just turns everything positive, right? A positive number stays positive, a negative number becomes positive. So for example, if I take the absolute value of -3, what do I get? 3. Or if I take the absolute value of 10, what do I get? 10. If I take the absolute value of 0, what do I get? 0. Everybody feel comfortable performing an absolute value on a number? Should be very, very easy, right? You're like, oh yeah, this is piece of cake, no biggie. So this definition here is kind of like a geometric definition, right? Because if I'm talking about, say, the absolute value of -3, well, here's 0 on the number line. 1, 2, 3 units away is -3. Everybody okay with that? Because we're relating it back to a number line. It's kind of like a geometric definition. Everybody all right with that concept? Another definition, this one is like the algebraic definition. We'd say that the absolute value of x is equal to, and then I'm going to draw a big squiggly bracket. This is what we're calling, or what we call, a piecewise function. And I'll explain why we call it that in a second, but that's what this thing is. So we call this a piecewise function because it has at least 2 pieces. And what the piecewise function is doing is it tells you to do one thing in one situation and something different in another situation. So the situations are described over here. And the x they're referencing is this x in our absolute value. So if we try to evaluate the absolute value using this definition, so if I say the absolute value of 5, well, the 5 in this case is greater than 0, correct? So what it tells me is the absolute value of 5 is just 5. If instead I wanted to look at the absolute value of -5, -5 is less than 0, correct? So what this tells me then is I want to do negative of -5, which is +5, right? So it's just like a fancy technical way of describing what it is that we said in words was, it just gets rid of the negatives. Okay? So don't be freaked out if you see this. It's just the algebraic representation for the absolute value gets rid of negatives. Everybody okay with that? So, huge, important rule to keep in mind. Absolute values do not distribute across addition or subtraction. By distribute, I mean if I have the absolute value of x minus 3, that is not the same thing as the absolute value of x minus the absolute value of 3. In fact, the absolute value of x minus 3, there's nothing more we can do to simplify that. That's as simple as we can make that. Okay? This is a big deduction if you make this kind of mistake on a test or something. Everybody okay with that idea? And you're like, I would never make that mistake. You just told me not to. Here's why students still make this mistake. Is that absolute values can be split over multiplication and division. So if I have something like the absolute value of 2x, I can say that that is the same thing as the absolute value of 2 times the absolute value of x. That is okay to do, which further would simplify down to just 2 absolute value of x. What about if they are in combination? Can I do anything to simplify this? Anybody got an idea here? Can I break up this absolute value? I cannot. The reason is that the times 2 applies specifically only to the x. In order to get this to a place where I can break up the x and the 2x, I'd have to do this. Not allowed. Right? Did you guys see that? Possible? I do not. Should we go to the bathroom? Yeah. Okay. I might die. Please don't die. However, what if we had something like this? Doesn't seem like this is any different, right? Not at first glance. Anna, please?
You can divide both sides by 2 and then maybe like distribute that.
Okay, so you have kind of the right idea. So there's not 2 sides to this, but I think I understand what you're trying to say. I think what Annalise is getting at is that because the 2 and the 4 both have a greatest common factor of 2, I can factor that off and rewrite this as 2 absolute value of 2 times x plus 2. And now, because the multiplication is happening before the addition in the order of operations, can split this apart and make this just 2 times the absolute value of x plus 2. So this is why this topic can get a little bit tricky for students. Yes? Yes. So that's where we'd stop. That's as simplified as we can go. Because again, absolute value of x plus 2, we can't break that apart. Questions so far? Okay. So that's about breaking an absolute value, splitting an absolute value apart. How about combining them together? What if I wanted to do the absolute value of x plus the absolute value of 2? Is that just the absolute value of x plus 2? Can I do that? That's bad. Just as an example to show you why that's not true, let's pick a value for x. Let's say x is -1. If I do that, on the left-hand side, I would get 3. Everybody agree with that? If I do the same thing on the right-hand side, I get 1. 3 and 1 are definitely not equal, right? So that's a nice little test you can do to check to see if the simplifying you're doing is okay to do. Pick a specific value for x. You might want to do more than one just in case you find like one instance where maybe like the two sides are equal. But for the most part, you should find very quickly that that those two things are not okay to do, if you're in question. What if I take the absolute value of x and add the absolute value of x? What about this? Can I add these together? Yeah. So the absolute value of x and the absolute value of x are like terms. So when I add them together, I just get 2 absolute value of x's. Everybody okay with that idea? What if I had 3 absolute value of x minus 6 absolute value of x? What would I get here? -3 absolute value x, yes. What do you guys think? So far, so good? Okay. So we'll do some more on simplifying kind of throughout this chapter. But I want to start talking about graphing now. So the parent function for the absolute value function is the graph y equals x. The graph y equals x has 3 key points that we're going to be concerned with. It's the points -1, 1, 0, 0, and 1, 1. So the graph of the absolute value function should look like a V. Everybody okay so far? This part of the graph, the point of the V, has a special name. Do you know what this point is called? Starts with a V. It's the vertex, is what that point is called. And we would call an arm of our graph. So in this case, the graph has two arms. You might refer to them as the left arm and the right arm, because they're meeting at the vertex. So, let's say that I wanted to graph y equals the absolute value of x plus 1 minus 3. To do this, I'm going to use what I know and my parent function to generate this graph. So the important part is that for a parent function of x, any member of the family can be written as a times f of x minus h plus k. And that we can transform our point from the parent function to the new transform location by using this transformation map. So these are going to be the two main tools that I'm going to use to do one of these graphing problems. So notice those things from last chapter that I said, like, I wanted you to memorize. The reason I wanted you to memorize them for the test is because we're going to use them over and over and over and over again throughout the semester. And if you don't memorize them, they'll kind of keep coming up to get you every step of the way. So if you didn't memorize them already, make it a priority and try to take a little bit of time and do some of that. So in our case, our parent function is y equals the absolute value of x. So in this specific instance, our general form is going to look like y equals a times the absolute value of x minus h plus k. So in this particular problem, what is our value for a, h, and k? What is our value for a here? 1 is correct. What is our value for h? -1. Remember, the h's are always the opposite of what they appear to be in the equation. And the k is -3. So my transformation map then that I'm going to write is going to be x minus 1, y minus 3. Notice how I omitted the 1 times y because it's just y. So what I'm going to use is I'm going to use the 3 key points from my parent function, and I'm going to apply this transformation. and then I'm just going to plot these three. Everybody okay there? So you see that what we're doing here is still the same thing that we did in the previous chapter when we talked about graphing functions in general. We're just now applying it to this specific type of function, which is the absolute value functions. The same techniques apply. We did everything the same way. We just need to be careful that we're reading the values of A, H, and K correctly. And we kind of remember these key points, right? Will those key points be the same for all absolute value graphing problems? Yes. You'll use those same three key points each time. So let's look at some observations we can make about these absolute value graphs. So when we say observations, really I'm talking about these ways to describe an absolute value function. So when we talk about the domain, what will the domain be in this situation? So if I look at this, there's no point furthest left, and there's no rightmost point. So the domain should be, correct, negative infinity to positive infinity. And what's wonderful is it's always going to be that for absolute value functions. All absolute value functions have the same domain. That's really nice. Massimo? Yep. You're welcome. Everybody happy there? Let's talk about the range here. Is the range always going to be the same? Definitely not, right? So remember, the range is like the lowest point to the highest point. If I look at this graph here, is there a lowest point on this graph? Yes. Is there a highest point on this graph? No. Is this the only way that this graph can be oriented? No. What other way could it be oriented? What was that, Nicholas? Good. So if the A value was negative, we could have a reflection across the x-axis where the graph is now pointed upside down. So what we have is two situations for the range. So we'll have a situation where the graph is a V, or the situation where the graph is a wedge. A Everybody okay with that idea? All right. If the graph is a V, there's a lowest point. Everybody agree with that? Like the one we circled right there. And that point is a point on the graph, but there is no highest point. So there would be positive infinity. The question is, what is that lowest point going to be? If I go back and I look here, this is the point, negative 1, negative 3, right? If I go back in, it's corresponding to this point, which is changed by the k. So the k value is going to tell me what that y coordinate for the lowest point would be. If the graph is a wedge-shaped, there's no lowest point, but there is a highest point. And again, that highest point, if the graph is wedge-shaped, is going to be defined by k. And we can tell if the graph is going to be V-shaped or wedge-shaped by looking at the sign of A. If A is positive, it'll be a V. If A is negative, it'll be a wedge. So if I go back and I look at this graph, do you guys see an increasing part? I see one increasing part, don't you guys? How many decreasing parts do you see? I see one decreasing part also, right? All absolute value graphs are going to have one increasing part and one decreasing part. The problem is if it's a V or a wedge, because again, we're going to have two situations. Actually, I'm going to format this a little bit differently. I'm going to do it this way. So if it's a V, we would be decreasing on this section, right? And if it was a V, we'd be increasing on that section. So notice that that vertex, when we found it before, was -1, -3. So the -1 is coming from this, and this -1 that's being subtracted from it is our h. So really, that vertex is going to happen at h, k each time. So we're increasing from either h to positive infinity if we have a V, or from negative infinity to h if we have a wedge. Yes, Tom? Of course. And then if we're decreasing, it's just the opposite. Okay with that idea? So this is really nice, right? We're coming up with some really general rules that we don't even need the graph of the absolute value function in order to kind of determine some of these intervals of increasing, decreasing, and domains and ranges and stuff. I can just look at the equation and figure this stuff out without even having to graph it. That's kind of nice, right? Man, guys. I guess we probably should have mentioned this earlier, but the vertex is always h comma k. Probably should have led off with that one. The end behavior, guess what? Two situations. Either both arrows point up, in the case of the V shape, or in the case of the wedge shape, both arrows point down. So let's take a look at the graph, or the function y equals -3, absolute value of 2 times x minus 1 plus 4. Yes? Yeah. Is that far enough? Okay. Yes, of course. Libby, are you all set?
Yeah.
No problem. All right. So, one thing I would notice before I get too far into this, can I do any simplifying to this absolute value? You should say yes. What you should notice is inside the absolute value, I have two things multiplied together. I have 2, and I have multiplied to that an x minus 1. Does everybody kind of agree with that? So let's simplify that. And that will simplify down to -6, absolute value of x minus 1 plus 4. Everybody okay there? What are my values for A, for H, and for K? What's my value for A? Close. -6. That's okay. The value for H? +1. Remember, the H's are always opposite of what they appear. And the value for K is 4. So without actually graphing anything, let's look at all the information, all the things that we can say about this. So first thing I can say, this is second hour, so you missed me. It was only by like 50 minutes though, so. First thing we can say is the vertex. I know the vertex is the point HK, so that's the point 1, 4. Everybody okay there? I can tell if this is a V or a wedge. In this case, what shape is it? Since the A is negative, I know this is going to be wedge-shaped. Everybody okay there? I can say the domain is always, for all absolute value functions, negative infinity to positive infinity. And now, since I know the graph is wedge-shaped, I can say something about the range. So I know that if I go back and I look at my list, my range is negative infinity up to k, and the k gets a bracket. So I have negative infinity up to 4 with a bracket. Isn't this kind of impressive that we're able to do all of this without actually looking at the graph at all? That's kind of nice, right? Okay. We can do our intervals of increasing and decreasing. So for our wedge, we are increasing in the beginning. So we're going negative infinity to h. Oops. And in this case, h is 1. And we're decreasing from h to positive infinity. And remember, the increasing and decreasing always have parentheses. And then our end behaviors, since this is a wedge shape, both arrows point down. So I can say the right end points down, and the left end points down. I don't know why I did right then left. That seems counterintuitive to me. Don't mind me, I'm on 3 hours this week. So look at all this information we were able to wring out of the equation just by knowing what we know about how the transformations of functions behave. We did all of this just by knowing how to find the values of a, h, and k. And look at all this information that we were able to glean. Now, if we wanted to still, we could certainly graph this. And to graph this, we're going to always kind of do it the same way. We're going to start with our 3 key points. And then we're going to write our transformation math. So this is x plus h, a times y plus k. And then just perform these operations. Everybody okay with how I'm generating these points here at the end? It's an important skill to have. Notice that I'm using that formula each time to do it. That's definitely something good to have memorized, because every time you graph, you're going to be using that same formula over and over and over again. not just in this chapter, but for all of our chapters moving forward. So once you've got it memorized, it's not like it's going to go away and not be useful for you. It'll be useful for you for really the remainder of this class. And even next year, if you take trig and free calc, you'll use almost the same formula. We add another type of transformation in there in that course, but it'll be pretty useful. So if I wanted to then sketch my graph, let's see, 1, 2, 1, 2, 1, 2, 3, 4, 1, 2, 3, 4. So I'm going to be plotting 0, -2, 1, 4, and then 2, -2. So I have this guy that's up and down, or has been flipped upside down. It's tall and skinny, so that's a vertical stretch. It's been moved right 1 unit, and it's been moved up 4 units. Which is exactly, if I was going to describe this picture, what I'd be saying, right? Ariana? Elena? Reflect x-axis? Yeah, again, if you have trouble reading my penmanship, don't hesitate to ask. I know it's not always spectacular. No offense taken. It's important that you can read what I'm writing. So if you have questions, make sure you ask. I can see that. Are you have a cold? Allergies? Life. Allergic to life. There's a cure. Might take a while to get there, though. That's dark. That's dark. All right. Now, let's bring it down on everybody. That's a big downer to end class with, right? Does anybody have questions about what we've done so far? Okay. Sure. That's an easy question to answer. Let's do one last thing. What we've been talking about so far has mainly been focusing from going from the equation to the graph. What if we wanted to go from a graph back to an equation? So let's say we have the graph here as pictured. So our goal is going to be to write some equation that looks like this. Everybody okay with that idea? So to do this, you need to find values for A, H, and K. Correct? 2 of the 3 are really easy to get. I know that the vertex is just the point H, comma, K. So in our case, what can we say H and K are? 1 and 6. Because this guy right here is our vertex. So that's 2/3 of the way done without really having to do anything at all, right? just had to identify the vertex on the graph. And that's not so bad. Our last thing that we need to do, though, is we need to get this value for A. We have yet to use this other point. That's the tool that I'm going to use to get my value for A. So let's just kind of write down where we're at to this point. So we figured out my value for H, and we figured out our value for K. And we have some point XY that we know is 0, 3. Well, if I look at my equation here, it has an x and a y in it, doesn't it? What I'm going to do is I'm going to plug 3 in for y and 0 in for x and use that to solve for A. So 0 minus 1 is negative 1. Absolute value of negative 1 is positive 1. And A times positive 1 is A. And if I subtract 6 from both sides, I get that A is negative 3. So I have y equals negative 3, x minus 1, plus 6. That's my final answer. Stretch. Questions on what I've done there? Elena.
Yeah, okay. Here's a question. Like, since we know that like one point is the vertex and then another point, and you know that since we minus we just like make it negative, and now we do all that.
So you do know from the shape of the graph, because it's a wedge shape, that the A value is going to be negative. You don't know that just making a negative of the y coordinate here is going to give you A. That just happens to be a coincidence this time. It would not be true in general. So, but it is a good check to look at the shape of the graph and go, this thing pointed down. I know my A should be negative. If you did not get a negative answer for A, you could definitely go back and look for something up. That is a good observation. The other part is just coincidence. Okay? Good questions, though. Good questions. Annalise. Yes, of course. Okay. So that's as much as I wanted to talk about today. So, again, we're going to be Unit 1, Module 2, Lesson 2.1 on the online textbook. And what I'd like for you guys to do is to do 1 to 11 odds, (12 and 13), yes, of course, 15 and 18. So I think that is, if I counted right, that's less than 10 problems there. Maybe exactly 10. 9. Yeah. So should not be too bad.